All right, so we are going to finish up this semester with a short section on parametric equations and graphs. And so this is sort of the other way of graphing things. So far we've looked at rectangular coordinate systems. Can anyone tell me the other common name for rectangular coordinate system? Yeah, Cartesian. There's so many different vocabulary terms here, but Cartesian is another way of saying rectangular, right? And last week we learned another kind of way to graph systems. What was that kind from last week? Yeah, precisely. We talked about polar graphs. And so we saw that some of the ways of writing polar equations actually made the equation a lot easier. So for example, if I had the equation r equals 5, can anyone tell me what shape that is? I had a polar equation r equals 5. Yeah, we would have a circle. Yeah. And where would the center of this circle be? The center, like the middle point. Where would the middle point of the circle be? Yeah, it would be at the origin. And what would the radius of this circle be? Yeah, it would actually be 5. Okay, it would be 5. And I think that's a little bit different. Some of you might be thinking about, like, if I did 5 cosine theta, something like that, we would also get a circle, but maybe that circle doesn't have a diameter or a radius of 5, right? And then one last do we remember question. Do we remember the rectangular equation for a circle with a radius of 5 centered at the origin? That was a long question. There's another version, right? If we write it in rectangular, for the same thing, the same picture that we get when we get r equals 5. Yeah, we could write it a really long way, right? Our x squared plus y squared equals r squared equation, right? And it's not necessarily that much longer, but it is a little bit if we think about it, maybe in the middle of a much bigger problem. Okay. And I noticed that some of you wrote about sort of the polar and parametric being used in calculus. And for sure, in calculus, mostly again in Calc 2, you get to see like, oh, what about the slope of these different points, or how much area is inside of this shape? And those are questions that you get to answer. Okay. And so all of that to say, today we're going to be learning about parametric equations and graphs. All right. And in particular, we're thinking about polar equations and graphs, so sort of show us one type of graphs and equations. But when we have parametric equations and graphs, those can be used sometimes in the same way, but also for cases where, just sort of like Dallas had written, maybe it looks more complicated in a rectangular equation format. So we change the way we write it to make the rest of the computations easier. All right. And so let's start with this definition here. So it turns out that a plane curve, right? So plane, not like the airplane in the sky, but a plane like sort of if we think about our two-dimensional plane right here, we have an XY coordinate, okay? So a plane curve is the set C of ordered pairs, f of t, g of t, where f and g are functions defined on an interval I. And so I know that's a lot of words, but what I want us to do is kind of think about it, what it looks like in addition to that, okay? And so all three of these right down here are examples of plane curves, all right? And plane curves in the sense that we have, we're gonna have some coordinates and we're gonna plot some points. And after we plot these points, we're going to get a shape. All right. Now, one of the things that makes this a little bit more interesting, as you can see when we're sort of tracing the curves, they don't go sort of like a straight line like we have. Oh, is that coming up? Okay, yeah, a straight line like we've seen, or maybe it doesn't even look like a parabola like we've seen, but these sort of look more like random motions, like they're not necessarily as structured in the same way as the curves we've seen in the past, okay? And so that's something we're going to see a lot of today. We're going to be looking at these curves that maybe look a little bit different than a lot of the other graphs we've seen. But one characteristic that all of these will have is going to have sort of a starting place. Like in this case, we're starting with little a. Oops, let's make that a little bit bigger. And we're going to follow a certain path along until we get to the end. Okay, so in particular, this is going to be different because we sort of have these starting and ending points, and we can follow these different paths. Okay, and so in the last two examples here, closed curve and simple closed curve, we have sort of a shape that contains some space. And so that's why we call it a closed curve, because there's sort of like this inside space here and this other inside space here. And then the last one, simple closed curve, we call it a simple closed curve because once we go around the shape one time, there's just one space inside. Okay. And so let's take a look at another definition, right? But I would encourage you to sort of like listen to these definitions now, make the sense that you can, but after we go through examples and stuff, go back to these definitions and really think about, okay, does this part make sense? Does that part make sense? What did we mean when we said f of t or g of t? What did that look like in the examples? Okay. And so in this case, we have C be the curve consisting of all ordered pairs, f of t, g of t, where f and g are defined on an interval, okay? But what is the parametric equations part? It turns out that the f of t and g of t, those are the things that we call parametric equations. And they're called parametric equations because we're involving this parameter t, all right? Now, I've said a lot of different words here, but knowing what you know about science and math, I'm wondering if anyone has any guesses what t might represent here. Right, we have a guess in here for time. Anyone else have any thoughts around that? T standing for time, agree, disagree, not sure. I would agree here that this parameter does, in fact, talk about time, okay? And this is not all of the time, but a lot of examples when you're looking at parametric equations in like modeling something, all right? And it could be in physics, it could be in biology, but we're often thinking, let's measure how things relate with respect to time. Okay, and so that's something I want us to think about, like all of these different pictures that we have here and all the different ones that we're going to generate. A lot of times we're modeling something that's happening over time. Okay, and so we might need sort of an X component and a Y component, or just two different components to describe what that looks like. All right, so let's start off by doing a little bit of graphing here. All right. And so we'll go through a couple examples where we are graphing. All right, so in this equation, we have x of t equals t minus 1. We have y of t equals 2t plus 4. And we go from -3 to 2 are our t values, right? So I've made a table already here for us to fill in. And if we could take a look at the first column is x of t, all right? Can someone describe what process I might do to complete this column for x of t? Right? How would we find all of these values for x of t? All right, we see plugging the t values into the, I'm going to guess you meant x equation. Yep, those letters are so close together on the keyboard, right? So let's go up. We're going to find our x equation. Whoops. X equation, x of t equals t minus 1. Great. So what do we put here? When t is -3, what is x of t? All right, -4. Great. Other folks chime in, help me fill out the table all the way down this column, right? What are we going to put in for our x of t's all the way down that column? Great. We take each of those values and we subtract 1. And we have our table, okay? So someone else that I haven't heard from yet, how do I complete the y of t column? Great, we are going to substitute as well. And this time we're going to choose that y of t equation. Wonderful. All right. Fill in this table for me. Tell me what values I should put in there for that y of t. And I know that Ian put in all of the values at one time. You can just say, oh, when t equals this, y of t equals that. That's also fine. Or Ian's already got all those calculations done and we'll do a quick check. I agree with what we have here. So -2, 0, 2, and 6. Nope. 4, 6, and 8. All right. So we're almost thinking about a very first time we started learning about plotting XY points, right? We've got a table, we fill in some values. All right, so I'm going to plot some points so that I can see what curve C looks like. All right, and so the first point I'm going to plot is the -4, -2. Now, I know this is at the top of the table, but can someone tell me why I'm going to start here? What else in this question tells me I should start by plotting the point -4, -2? It is the earliest time value. Exactly, right? When we look at this -3 to 2 for the time, it means we're really starting at -3. And so since these XY values correspond to -3, that's where we start, okay? So now I'm going to start here, and in order, I'm going to plot all of these points, and then I'm going to connect them with a line. All right, so I plot the points and I get -3, 0, -2, 2, -1, 4, 0, 6, and 1, 8. All right, and then I'm going to go ahead and connect these. Now, one of the things that I do not hope we do is something like this. Why would I say, I hope we don't do this? Like, isn't that how we drew all the other graphs like ever in our whole lives? Why would I say don't do this? Because they should have a start and end point, okay? And so this goes back to that interval. We start at -2 or -3 and we stop at 2. And so we don't want to draw the arrows because the arrows would tell our reader that we think that it goes on forever and ever. That's not what's being communicated here, right? So we want to make sure we leave it as a line segment, not a line, right? So that's the first thing I want to point out. The second thing I want to point out is this part. I type these directions all the time and people don't read them. Including arrowheads to indicate the direction in which P of X, Y traces the curve. So this is where I started. This is my first point. And then I went all the way through until T equals 2. And this was my last point. And so all we need to do to fulfill that last requirement is we just need to draw little arrowheads in the direction that I want. Definitely got a little lag here. There we go. All right, so we want to just show the direction, but we don't want to sort of indicate that it keeps going forever like that. All right, so those are similar but different things. Does that make sense to folks? Having the arrows, but not extending it beyond the start and stop time. Okay, good. All right. And so just to make this a little bit more clear, we have 0.1 here, we have 0.6 here. This is my starting point. This is my ending point. Okay. That's a great question. I would say enough to show me the direction. If you do, probably at least 2, but it doesn't have to be this many. All right. It's more important that you do actually draw them rather than how many. Great. Let's take a look at example number 2 here. All right. And so let's go ahead and take a moment. Maybe I could ask some of us to choose the X equation to help us fill in our X of t column. And if I could ask other folks to choose Y of t and just plug in the Y numbers, all right? So before we begin, if you could just type into the chat whether you were choosing X or Y, so we can get sort of figure out who's doing what, that we have at least a couple people doing each, all right? We've got 2 takers for the X's. We got 1 for the Y, all right? Great. Once you've picked yours, if you could go ahead and just start plugging in the values, and then we'll list those out, see what we get. Right. Let's see, we've got t equals 3. We have x equals 6. I would agree with that. All right, let's make sure we agree. Ellie, let me know if you agree with Ian's numbers in there when you get a chance. T equals 2, x is 1. I agree with that.
I got the same as him.
Wonderful. -3, -1, 1, 3, 5, and 7. All right, and if we've got the first one, I believe that's correct for -2. Oops. All right, I'll start plotting some of these points. We've got 1, -3. We have 1, 5, and 6, 7. T of 1, x equals -2. All right, so that gives me -2, 3. And 1, -2, -3. Thank you, Melissa. And we've got -2, -1, and -3, 1. All right. Nice, nice. All right, so when we look at these points and we imagine that they might be connected to each other, I think I drew something wrong, by the way. 1, 5, -2. Yep, -2, -1. All right, so if we look at these points and imagine a shape that goes through them, how would you describe that shape? Right, like I feel like if I had asked you that same question before we did 1, folks would have been like, it looks like a line. What kind of shape might we imagine number 2 to be?
Something like a parabola.
Yeah, I like that. Maybe a parabola, maybe a hyperbola. Okay. Now, in order to be a hyperbola, usually we have 2 different branches, right? And so we might have something kind of like this. And it's hard to tell from here which one it is. It turns out that given the setup of the equations, and we'll talk about this a little bit later on, that we do in fact have a parabola. Okay, so we have a sideways parabola. But just like our line above was actually a line segment, we have very clear starting and stopping points. And so when we connect these, we want to make sure that we don't go beyond that ending point. And same thing, we don't go beyond the starting point. Okay. Now to Matthew's question earlier of, how many arrows do we need? I would say 1 here is probably not enough, because if you put 1 facing this way, right, we want to also make sure our reader knows that as we turn the corner, we're still going in that direction. Okay. And so whatever you feel like makes it look like enough, but you don't need to draw like, 15 arrows or anything crazy like that. Okay. And then again, we don't want to extend it beyond to draw the arrowheads here, because we have a start and stop time. All right. All right, let's try one more example like this. And if we could do the same thing, type into the chat the y's, or you're going to work on the y's, or you're going to work on the x's, just to make sure we've got enough diversity in who's doing what in the class, and then we'll fill in those values. Now, I would encourage you to make sure you're looking at these right here. All right, so I've given you specific t values here. And so we want to keep in mind that some of these we might have to be a little bit careful with when we're doing our arithmetic. Right, let's see what we got here. -2, -1, 0, and 1. I agree with those values. 2, 3, and 4. Nice teamwork. All right. Notice nobody really wants to do those y values, but it would sure be helpful if we could get some of those in here as well. All right, I know it's fractions, I know it's early in the morning, but what better way to build that mental strength around fractions? All right, I agree, 0 for the first one. Go ahead and start plotting, -2, 0. -3/4, I agree. So -1, -3/4, -1. All right, 0, 1. I argue that we know what 1/2 and 1 are going to be. Yeah, why is that though? How did I know that before I even actually plugged in the values? Yeah, because we're looking at the number squared, right? We're doing t squared. T squared doesn't mean, it means that if I take a positive number and I square it, or I take a negative number and square it, I'm going to get the same thing, right? So sometimes when we're looking at tables, we can use that as a shortcut and say, oh, I know these two are going to be the same. I know these two are going to be the same, right? And I believe the last two here should be 5/4 and a 3. Can anyone confirm that for me? Cool, cool. All right, so 3, 5/4, and then 4 and 3. And what kind of shape are we seeing here? Yeah, I agree. I start to see this part of a parabola, right? It's not the whole thing, but if I had more t values, I could see that it would be something like a parabola. Right? And so we connect the dots again. And we put in enough arrows, not too many, but however many we see fit, so that our reader can see the direction of what's happening here. Okay. All right. How are we feeling with all of this? So far, so good. Give me a quick thumbs up or something. Okay. Well, all we've really done so far is just figure out like how to use some skills that we know, like here's a table, here's some equations, and let's plug in those numbers and see, just to see how graphs like this can be created. Okay. And so if that feels good, that is excellent. And what I'd like us to do now is we are going to take a look at one last graph. I think this will be the last graph that we look at before break. All right. But this is going to require us to go back into our unit circle memory and think about things a little bit. But for the sake of time, I think what I'd like us to do is to think about using a calculator. All right. So let's see. I wanted to show you something on Desmos, but let me see if I can share a different screen right now. All right. Can you folks see Desmos right now?
Yeah.
Yeah, okay, cool. Boop, 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 boop. All right, so we've been using Desmos a lot for graphing, right? We know we can type in an equation, like if I typed in y equals x squared, I could get a graph. And if I wanted to graph a different one, I could do y equals x squared minus 2, or x to the minus 2, something like that, right? And so you can start to graph a bunch of things, and it's really nice and handy to be able to do that visually, right? But there are some other features. I know we've talked about how you can like hear the graph, which I think is pretty cool, how you can see the intersections between things. But there's a new feature I thought we would share since, you know, it's Desmos and I think it's a beautiful tool. And one of the ones that we haven't really used is this little plus button up in the left-hand corner, right? So you see when I hover over the plus button, it says add item. So I'm going to go ahead and click this. And by default, usually we have f of x, like type in an equation or an expression, it'll give you a number or it'll give you a graph, right? But what I want us to do right now is we're going to go ahead and click on table. And so if you want to, you can sort of follow along on Desmos on a different browser on your home learning environment, right? But if you want to just watch, this is fine as well. So we can click on table. And so what happens is in that place where we type in the equations, we can actually type in and get a table of values, right? So if we're looking to plot something, it might be really nice to just have a table. And so I'm going to change this to be x. And the y one, I'm going to change it to an equation. I'm going to make that 4 cosine x. Okay. And so if I plug in 0, it tells me automatically that I get 4. Okay. And so where am I getting these? If you look at your example 4 on the notes, right? I've got 0 and I've got 4 as the first column there. And my pink equation, which maybe we can change this to red. That's the closest we have to pink here. But we can also put in another column that, what should I type in this third column here? If I want to make Desmos give me the table. Great. Can you be more specific though? Because it won't know what y of t is for our particular problem. Anybody happen to have their notes available on their screen or maybe a handout, like a printed copy? All right, we're on example 4 right now. You're good. I don't think I was very clear about that we moved on from example 3. Yeah, 4 sine t, right? So that's where I got the 4 cosine t, because if you look at my x equation in number 4, it's 4 cosine, but I can also do 4 sine x. Okay. Now, this is going to give us 2 different graphs. So that might not be really helpful for us, right? Because you can start to see we've got a red dot and this black dot here. Maybe we'll change this to blue to match the graph in the notes, but we have the red dot and the blue dot, and they're graphing them separately, right? They're graphing them separately. And so what we're using this table for right now is really just to help us fill out the table in the notes, all right? So what would the next x value be that I want to see what I get for my 4 cosine x and what I get for my 4 sine x? Yeah, so let's type in pi over 6 and bam, it gives me the values that I want, okay? And so let me do a couple more, pi over 3, pi over 2, right? That should be the first 4 values in here. Now, I know that the graph is not looking like how we would graph these, okay? But I just wanted to show you that we can use this table for this. So we're going to come back to Desmos in a second. I will show you later how you can graph parametric equations on Desmos, because you can. All right, and so it's an important tool to know. It's a great way to check your answer on working through things. Okay, so let me reshare my other screen. All right, but if you have Desmos open, if you wouldn't mind sort of typing in a bunch of angles and then getting those values so we can fill in that table together, that would be wonderful. All right, so let me stop this share. So I'm going to copy down the first few values that I see here. We've got 4 and 0. I'm going to round a little bit because I can't necessarily graph super fine decimals on the grid right here. Okay, so I'm going to call this one is on Desmos, it says like 3.464, but I'm just going to call it 3.5. Okay, and we've got a 2 and a 0, and then we get 2, 3.5, and 4. All right, so I'm going to graph these points real quick and let's see what we get. So we have our x of t, which again we got from up here. We got our y of t, which is going to be that second column. And so the first point I'm going to plot, which is not what Desmos did. What's the first point I should plot?
Well, it would be 4, 0, right?
4, 0. I would agree with that. All right. So we've got 4, 0. That's when we're starting our time. Okay. Let me plot the other 3 points. So I've got about 3.5 and 2. Oops. 3.5. 3.5. 2. I've got 2 and about 3.5. I've got 0 and 4. What shape would you imagine if we plotted the rest of these points? What do you think our graph is going to look like over here? Do we have any predictions? Okay, we have a guess for a circle. What makes you think a circle? Okay, so if we zoom in over here, we might notice that there's like, I don't know if this is the center, but if I go out 4 units in this direction, I get a point. And if I go 4 units in this direction, I also get a point. So it seems reasonable to guess that if I went in this direction, I would go out 4 units. I think that's a pretty good guess. What angle would I plug in for t if I wanted to see the point along this direction? Right, so what value should t be to see what's happening specifically in this direction? I agree that 2 pi over 3 would be a great next value to put in my table. But what if I wanted to skip a few and just check? Ah, Matthew, what makes you say pi? You're absolutely correct. Right? Why pi? How would someone know to do that? Okay. I mean, I believe it's a quadrantal angle, but how come I wouldn't, if I wanted to check this direction, how come I wouldn't try t equals like 3 pi over 2? Yeah, because that's not where, right? In this direction, I know we're on a rectangular coordinate, but if we imagine our unit circle, right, this is in the direction of pi. And maybe that was just too straightforward of an answer for you. You're like, obviously, because pi is in that direction, but I just wanted to make sure we knew like everyone could see that thinking, like, why do we choose pi next? Because if we get 4 out, there's a pretty good chance that we're going to end up with a circle. Okay. And so if we type pi into that Desmos table, I believe we get -4, 0, right? And that would put us right over here. If we did all the other points, we would also find that I believe this goes to -2, -3.5, and this would go to 3.5 and 2. And so we would end up with something like this and like this. And it sure looks like that was a good guess that we're going to end up with a circle. Okay, so I will draw a circle in here. It's not going to be super pretty, but I will draw a circle in here. But as I'm drawing this circle, think about where I should start my arrows, where I should stop, and which direction the arrows go in. Okay, so I'm going to plot a few more points. And while I'm doing that, take some time to think about what direction my arrows should go in. Oh, that's not right. Right? So which direction should my arrows go in? They should indeed go counterclockwise, all right? I'm gonna try my best to draw this, but I'm gonna start right over here, right? This was the first point I plotted, that's where I'm gonna start. And the next point I plotted was over here. So that's the next place I'm gonna go, right? And then I keep going, and this is gonna be a pretty horrendous circle, but you get the idea, right? And so when we connect these, we do want to make sure our arrows tell our reader that we're moving in that counterclockwise direction. Okay. So sometimes you can get shapes that are closed like this one, right? Closed in the sense that we have one space in between. That's that simple closed case. But we might have other options where we end up with a shape that kind of looks like the infinity symbol, right? Or, gosh, I don't know. Anybody think about one of these? Right? We learned about those in polar graphs, but we could certainly use parametric graphs to describe that as well, okay? And so I won't make us fill out the rest of the table here, but there's space there for you to, in case you want to practice your Desmos skills or just to convince yourself that that second half of that circle actually does appear, okay? But before we go on break, I want to use this as a bridge to the next topic, all right? So far we've said, let's graph things using a table, right? Plug things into the table, we're good to go. There's a second method though, right? As we've seen by now, usually if there's one method, there's more than one method. And sometimes knowing the connection between those two methods is actually the key to finding success in a lot of the problems, okay? And so in example 5, it says, let's eliminate the parameter to rewrite our equation in rectangular form, okay? And so here's what this means. In rectangular form means eliminate t's, all right? And the second thing it means when someone says, rewrite our equation in rectangular form, it also means condense equations into a single equation. Right? Condense equations into a single equation. And so what did we start with here? We started with x equals 4 cosine t and y equals 4 sine t. All right. And so we have two equations, right? We have our blue one and we have our pink one. And I want to get rid of the t's, and I only want one equation. I don't want two. Okay. So just like we did with polar equations and even way back when with systems of equations, I would love to hear your ideas. What are some ideas we have on how we could get rid of the t's and only have x's and y's in our equation? Okay, so let's try that. Let's see, right? The worst thing that we can do is be like, ooh, that's not going where we want it to go. And that's fine, right? So let's divide by 4. So if I divide this one by 4, I get x over 4 equals cosine t. And over here I get, whoops, y over 4 equals sine t. All right, what do we do with that? You said also take the inverse. Do you want me to take the inverse of both equations or just one of them? Okay, let's test it out for x. So if I take the inverse on this one, what inverse function would I use? Okay, nice. Okay, so we would have inverse cosine of x over 4 equals t. All right, what would we use if we wanted to use the inverse trig function on the blue equation? Inverse sine, right? So inverse sine y over 4 equals t. Okay. Everything we have here so far is mathematically valid. What could we do from here? Oh, we can set them equal to each other, right? We have t equals and t equals. And so we can actually say that sine, oops, goodness, cosine inverse of x over 4 equals inverse sine of y over 4. So did we achieve this goal? Did we eliminate the t's and condense equations into a single equation? Yeah, we did. Okay. There is nothing mathematically wrong with this. Absolutely nothing. Okay. Unfortunately, you will not see this in an answer key. Okay, which doesn't mean that it's wrong. So I just want to make that really clear. What we have here is mathematically correct. You have technically eliminated the parameters to rewrite the equation in rectangular form. You have no more t's, you only have one equation, and it has x's and y's, okay? But when we come back from break, all right, we're going to talk about maybe a more conventional way that we typically eliminate these parameters, because one of the reasons we want to eliminate the parameters is so that we can see, is this like y equals x squared? Is this like y equals mx plus b? Like, we want it to be in a form that we already know so that we can be like, oh, it's that shape, or oh, it's this shape, okay? And so with that cliffhanger, let's see, it is 10:31 right now. Let's be back at 10:45, and we will pick up here, all right, where we're going to figure out a more conventional way, which is to say, this is not bad. It's just one that we probably won't encounter that much, right? And so we'll come back, we'll do a few more examples of that. We'll talk about some patterns, and then we'll call it a day. All right, so I'll see you folks back here in just a little bit. And so before break, we took a look at some suggestions based off of tools that we know on how we could fulfill the requirements of eliminating parameters, which is no more t's and only one equation, right? And I said, this is great. Everything here is mathematically accurate, and it's not quite what we would do conventionally, because sort of another secret goal here in eliminating the parameters is not only do we want to eliminate the t's and condense equations into a single equation, but we also want to find a, and I'll put this in quotes, a familiar form. All right, so our third goal, which is definitely one we still want to consider, is we want to make it into a familiar form, something that we can look at and be like, oh, yeah, that's a parabola, or oh, that's a y equals mx plus b, okay? And so let's sort of divide our space over here and think about other things that we might know, okay? And so one thing that I actually really like, we're actually going to be able to take this first step. Give you a chance to show up. Yep, we're going to take this first step and we're going to use this first step. All right. So that suggestion of let's divide by 4 turns out to be quite helpful. Okay, we're going to keep that. What we're going to do differently, though, is think of another tool in our toolbox that relates cosine and sine. All right, so let's think back into maybe the last unit. What do we know in terms of identities about cosine and sine? Right. what are some identities that we know about cosine and sine? All right, these are all wonderful ideas. They are, okay. We've got SOHCAHTOA, something that relates cosine and sine for sure. We see a fraction, that's a super valid guess. X equals r cosine theta, right? Trying to think about our polar coordinates, okay? Co-functions of each other for sure, okay? All super valid, and I love that we can think about so many examples. Give me some more. What other relations do we know that, or identities do we know that relate cosine and sine? Tangent does have both of them, yep. All right, what else? There was one that we used a lot when we were doing like proving or verifying identities. Okay, great. So I know that sometimes when you're looking at a math problem that you've never really seen before, and you go through this process, right? And how many of us have sat there and like answered one of those? We're like, oh, it's SOHCAHTOA. And then we just get so fixated on that we can't really think about other things, right? And so it turns out in this case, SOHCAHTOA is not particularly useful in trying to find a familiar form. Okay. And so I think a lot of times we're like, well, that was my idea. I don't know anymore. And so what I really like about this conversation we've just had is people are throwing out a bunch of different things, right? From the polar units all the way back to co-functions, all the way back to SOHCAHTOA, sum and difference, right? And it turns out that what happens is like when you see people work through these problems and you're like, how do they know to use this one? There's so many identities, right? A lot of that comes from the experience of thinking through these, having that list and being like, okay, all of these work. Which one have I seen before that might help in this case, all right? And so this will be the first time you'll see this, but the Pythagorean theorem is actually the one that we want, even though this is a cosine, not cosine squared, and even though this is a sine and not a sine squared, okay? So here's how we're gonna use this, all right? We're gonna say cosine, how do I wanna write this? Cosine squared t plus sine squared t. What can I say that is equal to? Okay, I can say that's equal to 1, right? Now, what's another way I could write cosine squared t? If I want to really see what it means to say cosine squared, how might I write that? cosine times cosine, right? Or we could even say cosine squared. That's really what we're doing. Yeah. And same thing here, we could write this as sine t squared. Okay. Now, if I write it like this, I might notice, oh, I have an expression for cosine t, right? Somewhere on this page, how else can I write cosine t? Yeah, x over 4, right? X over 4 equals cosine t. That means everywhere I write a cosine t, I can put x over 4. What can I put in place of sine t?
Y over 4.
Y over 4 squared equals 1. Okay, so all I'm doing is taking my rewritten terms. Oh, I'll give the screen a little bit of time to catch up. These rewritten terms, right? We divided 4 over, and then we were able to substitute it into one of the identities that we know. Okay. Now, before we keep going, because I think we always ask a good question. Lately, some of you have been asking like, oh, should it be implicit or explicit, right? So let's go back to our picture for a moment. We came up with a circle. What was the radius of this circle? 4, right? And so if I were to write this equation in polar, what would my equation look like? Great, r equals 4. Wonderful. What if I asked us to write this in rectangular? Great, x squared plus y squared equals 16. Okay. So let's keep that equation in mind, right? X squared plus y squared equals 16. If someone walked up to you on the street and was like, x squared plus y squared equals 16, tell me that radius, you would be like, oh, it's 4, right? It's a familiar form for us. Familiar form. Okay. How do we get this into that familiar form? Well, I argue that we can do this. And then we just have one last thing to do in order to make this look like the familiar form, right? If we multiply everything by 16, x squared plus y squared equals 16. Okay. And so I know that these are more lines, and maybe these lines are like, well, I didn't think about it that way. Like, why can't I do the other way, right? And the question here is really in that last one. We want to tie this back to a familiar form, something that if we hand to another person, they'll be like, oh yeah, x squared plus y squared. I know what that is, right? Whereas if someone was like, inverse cosine of x over 4 equals inverse sine of y over 4, you would be like, I don't know what that looks like, right? That's less familiar to us. And so we want to make sure that as we eliminate parameters, we eliminate the t, we get a single equation, but we also get it into a familiar form. Okay. All right. Let me zoom in on this page for a moment. Are there any questions about example 4 and 5 so far? All right, so we're gonna spend a lot more time decision making now, okay? So hopefully we're all like, yes, decision making, the most important thing we could learn in mathematics is that logic piece, right? I know that can be overwhelming, but it is something I hope we start to embrace. But we're gonna take a look at a few examples where we again have choices to think about like how we might best do this, okay? And so let's go ahead and start with example 6. All right. So you'll see here that I'm like, I don't want you to make a table. I want you to eliminate the parameters. I want you to get a familiar equation here. Okay. And so we have two equations. X of t equals negative t, or negative 2 plus t squared. And separately, we have y of t equals 1 plus 2t squared. Take a moment. Think about what we might want to do to get an equation that has no more t's, is only one equation, and is something familiar to us. Okay, and so if we wanted to isolate t, what would that look like, right? Let's take these ideas, let's try them out. I have the benefit of having a tablet so I can shrink work, right? I can erase work without too much effort. So it's okay if it doesn't lead us anywhere, but how would we do that if we want to isolate t first? Okay. So it looks like you're taking this one and you get x equals negative 2 plus t squared. So it looks like you're adding the 2 and then you get that. Okay. All right. What would we do with that? Ooh. Let's say we went all the way down to x equals or t equals square root of x plus 2. What would we do with that? Okay, do the same thing for y. All right, so y equals 1 plus 2t squared. Y minus 1 equals 2t squared. Y minus 1 over 2, and the square root of that equals t. Okay, now what? Okay, and so we'll get square root of x plus 2 equals square root of y minus 1 over 2. Great. I think you've achieved that goal, right? Now we're trying to achieve that third goal, which is make it familiar. So now we're going to square both sides. Times 2. Okay. Looks like we get a line, right? That's familiar to us. Now, I would say that there is, again, nothing mathematically wrong with what we've shown here. Everything is mathematically accurate. One thing I noticed though is Ellie's comment a little bit a few minutes ago. Thank you for being patient. You sort of highlighted this step, and I'm wondering why you did that.
Like, why did I isolate t first?
Yeah.
Squared. I was thinking maybe I could replace t squared with something.
Oh. Okay. So you know how down here we got t, and so we set them equal to each other, right? If you have a t squared and a t squared, you can actually set those equal to each other right off the bat. X plus 2 equals y minus 1 over 2. And so you're taking the method we did before, but you're cutting out 2 steps that we didn't really need, right? Because we square rooted it and then we squared it. So we sort of got back to where we were going, okay? Now, do I expect you to know that the first time through a problem like this, that, oh, there's a shorter way? No, but I think it's something to think about, right? Like, it isn't that we want to show the least amount of work. That's not necessarily the goal, but the goal rather is to think about how can we get to that familiar form most efficiently, right? We don't want to have to like square root and then square again because it took like 3 extra steps, right? So I would say, yeah, 100%. If you see that you have like a t squared and a t squared, you could set those equal to each other. You don't have to do the square root and then square it again part, okay? And so based off of this rectangular equation, right, and I think I sort of gave this away earlier, we might recognize that this is going to be a line, right? A line. So how in the world do we sketch this graph? Y-intercept at 5, okay? I agree with that. Yeah, and then rise of 2, run of 1, right? But when we draw this, we'll end up with sort of this line that goes forever and ever. But I argue that this is actually not what the graph looks like. Okay. I think part of this is the graph. And I want us to think about which part it's going to be. Okay. And so let's go back to these equations for a moment. X equals -2 plus t squared. What is the smallest value that I can get for X? What makes you say -2? You're correct. I want to know what makes you say that. Okay. So this t squared is always going to be what value? What kind of value? It's going to be positive, right? So the smallest X can be is if we add nothing to -2, okay? What is the smallest value we can get out for Y? I think there's actually a smaller value you can get out. Is there? Let's write down these values. Ooh, smallest x value is -2. Smallest y value is 1. How did we get 1? I think we could say by similar reasoning, right? The smallest this can be is 0. So 1 plus 0 is going to give us that bottom bound, okay? So it turns out, my friends, that this curve actually starts here, okay? This is the smallest value. So we would not have this part of our graph. We would only have the purple part. And furthermore, what happens because of that thing with symmetry and squaring a negative number makes it positive, like Ian had brought up earlier, means that our arrows actually go this way. So it comes in first and then it turns back around. So it's almost like a boomerang. You're going to go in and then come back out. So even though it looks like a line, it's really 1, 2, and does not go past that point on the bottom. Okay. This is really helpful if you're going to model situations in like biology or physics. You want there to be a certain stopping point or turnaround point. It's helpful to be able to control the parameters so that that happens. Okay. All right, let's try a different example. And let's think again about possible moves, right? This is our x, this is our y. What is the least number of moves we can make to A, get rid of the t's, B, have a single equation, and C, have a familiar looking equation? Square the x. So x equals square root of 2t plus 4. All right. If I square it, I get this. Let's think for a moment. Okay. We want to do this in the least number of moves. I argue that if we isolate t, we're going to end up in the same situation we did in example 6. Where we like did something and then we undid it.
Can we isolate t on both and then set them equal?
We could isolate t, but I suggest that there is a faster way to get to what we want. Oh, all right. Y equals 2t plus 1. Matthew's suggestion is we add 3 to both sides. Okay, that's in our toolkit, right? We can do whatever we want to both sides of the equation. Y plus 3 equals 2t plus 4. Why is this method going to make our lives a lot easier? I argue we don't need to isolate 4. We can mathematically, for sure, we can isolate it. Ah, there it is. 2t plus 4, 2t plus 4. If x squared equals 2t plus 4 and y plus 3 equals 2t plus 4, we have x squared equals y plus 3.
Wait, why did we add the plus 3?
What do you mean?
Why did we do plus 3 and y?
So let's see. Matthew said because 2t plus 4 is in both equations. So how do we make 2t plus 1 look like 2t plus 4? Right, we can just add 3 to that. 1 plus 3 gives us the 4. Does that make sense?
Yeah, I just wouldn't have thought of that, I think.
And actually, Matthew, you should take this for what it is. I don't think I've had a student approach it this way. So I think that's really clever. Okay. I think that most folks would have thought, maybe I just subtract the 4 over so that I can match this 2t. Does that make sense? So if we had gone with the original suggestion of get t by itself, you would divide by 2, but then you would multiply by 2 again here. So that's sort of that same idea as like the squaring one, where we like took the square root and then we squared it again. We basically get back to the same place. Okay. And so I think one thing is really clear. A lot of us have had teachers who've trained us to do like very specific methods, right? Like getting all the way down to t equals something so that we can set them equal to each other. And there's nothing wrong with that. It'll always work. And I bet for some of us who are ready to sort of move on, embrace a lot of the higher concepts, what happens is we don't want to get stuck in some of this like work that isn't actually necessary, right? So it's okay to sort of think outside the box a little bit, as long as your methods are algebraically sound. Right? It means you're not doing any illegal algebra, like square rooting a sum of things or something like that. Okay. All right. So we get x squared equals y plus 3. I would say we could do one move to put it into a more familiar form. And in fact, yes, I would say y equals x squared minus 3 would be a more familiar form for both you and the reader, right? For those of us who are in Math 116, we know this is a parabola and we move down by 3. And so that's a lot easier to think about a graph instead of saying this kind of weird looking thing. Okay. If I plot my points, I won't plot all of them right now because I think we feel good about the plotting. But if I were to plot the points for this graph over here, what should my starting point be? Or how would I find my starting point? Rather, that's a better question. Mm. Well, I think this question reads a little bit differently than the previous question. Maybe we put those together on the same screen. Ah, okay. So up here, we had T in R, right? This is the same thing as writing T, that sort of roundy E, and that's how I write the script DR because I don't have a really good script DR, but that script DR is saying that T is all the real numbers, okay? Whereas here, oh, I've given you an interval. So I've told you where to start and where to stop, okay? So to find the start, you would take T equals -2, and you could plug that into your pink and blue equations. And to find the end, you could plug in T equals 6 into your pink and blue equations, and that'll tell you where to start and where to stop. All of the points in between, you could graph using y equals x squared minus 3. Okay, so we sort of blend a lot of these processes. We say, I know we need to know where we start and end, but I don't want to plug everything into like a square root and like that kind of formula. I could just plug everything in between into the y equals x squared minus 3. Okay. So I'll leave you to graph this piece on your own time. It's okay to check with me if you're like, I don't really know if this graph looks great, but I just did want to point that out, that we can sort of blend those options and have some choices. Okay. All right. So let's do this. All right. We're gonna finish off today with these 4 examples right here, okay? And so it's a mix of different parametric equations. And so all of these are meant to highlight specific strategies, okay? So I tried to pick ones that represented like the most common strategies so we could talk about those. Let's see, let's pick which one of these 4 look the most straightforward. You're like, I think I could do that when I have some good ideas around it. All right, and let's kind of start there.
9 and 11 look straightforward.
9 and 11 look straightforward. Great. Does everyone agree with that? All right, I got 1 agree. All right. Okay. So let's just talk through number 9 for a moment. All right. What would be your strategy to get an equation in rectangular form in the most efficient way possible? And I'll give you think time. It's not easy to look at a problem and think about it right off the top of your head.
I think here we can easily isolate t and set them equal to each other, because in the y one, you just have to move one to the other side.
Nice. I would say you could isolate. Let's see, we have some other ideas in here. -1 for the y, +2 for t, and then times y by 3. Okay, let's try that. Y -1 equals t, but we have x equals 3t minus 2. So there's actually one method that we haven't quite talked about, all right? I agree, we could multiply this by 3. But why would this not work as well as it did in the previous case? And if I multiply by 3, I get 3y minus 3 equals 3t. So I get like 3t minus 2, but I just get a 3t over here. Okay, so maybe that doesn't work quite as well, but what we can do is actually do some good old substitution. All right, so I think sometimes we forget that method, but I have t. Everywhere I see a t, I can write y minus 1. Make sense? If it does work to be clever, right, where I could multiply by something and all of a sudden both the sides are the same, great. But if it doesn't, this is sort of a nice medium where I didn't divide this by 3 and get some weird fractions and then set them equal to each other. But I used a different skill, right? Where I said everywhere I see a t, I'm just going to replace with another way of saying t. And now I have at least an equation, but this I can write in a way that is more familiar, right? So I could add 2 to both sides. I could divide by 3. And finally, I could add 1. And all of a sudden, I have very clearly a y equals mx plus b situation. Okay. So lots of different tricks that we can try. Okay. How would we approach 11?
Could we use the Pythagorean theorem again?
Okay, great. I like that, right? That looks familiar. All right, well, how did we set up before we used the Pythagorean theorem?
We divided the coefficient for it.
Great, so we could have x over 4 would be a sine t, and y over 3 would be cosine t, right? And then we could say sine squared t plus cosine squared t equals 1. We know that's true. Now we plug in the things. X over 4 squared plus y over 3 squared equals 1. Dig back into your brain. This has been a really long time. But what shape is this?
A circle.
Ooh. Yeah, it's
Oh,
not.
yeah, because A and B are different.
Yeah, because A and B are different, right? So if I wanted to write this in a quote unquote familiar form for the reader, how should I simplify? Great, so x squared over 16, or could probably just leave it as 4 squared, y squared over 3 squared equals 1, right? And as soon as we've done that, it would be not too bad for a reader to say, oh, this is the ellipse. And furthermore, if we wanted to give them a picture for this, see how much we do or don't remember about this, how would I sketch this? We only need 4 points. How would we sketch this?
So, I mean, yeah, for X, you would go 4 like units away from the center on the X-axis. And for y, you would go 3 units on the y-axis.
Wonderful. Right? That's not the prettiest ellipse there ever was, but it gets the idea across, right? That we go 4 units out in the x direction and 3 units out in the y direction. Okay. So these two, I would say, super great job in identifying things that feel familiar to what we've looked at so far, right? And I think 8 and 10 are definitely a little bit more like, because they're dealing with things like square roots and log and e, right? There's so many of those different types of equations. And so it might be a little bit harder for us to wrap our brain around, okay? But I want us to try it out, to see like what kinds of algebraic tricks do we know? What do we have at our disposal, okay? And so let's take a look at number 8 over here. What might we do to write something? Maybe we don't know yet if it's familiar or not, but how would we get this so that we have a one equation with only x's and y's at least? Maybe 1 over e. Tell me more about that. What do you mean by 1 over e? Are you saying that we should rewrite this one, the x one? Okay, so maybe we don't remember a lot about e's, maybe e's scare us, but maybe one of the things we do know is like what to do when we have a negative exponent, right? So we could write this as x equals e to the negative t, or x equals 1 over e to the t, right? That could be one way to write it. What would we do from here? So like multiply both sides by e to the t and then divide by x? Yeah, I would agree with that. Okay, so let me just do that step by step. So in case you're not sure like where it comes from, right? I'm going to multiply both sides by e to the t. So e to the t x equals 1. And I want to get e to the t by itself. So e to the t equals 1 over x. Okay. What can I do with this e to the t? I could divide this by 3, right? This equation, whoa, is really saying my end of the semester handwriting is really, okay, let's do that again. This is really saying y equals 3 times e to the t. So I could divide by 3, but I bet we're going to have to multiply by it again later, right? And so let's steal this idea from number 9, where we're like, let's just substitute what we know. We solve for one of the t's, that's enough. Let's just plug it into the other equation, okay? And so we'll get y equals 3 times 1 over x. And another way we can write that is y equals 3 over x, okay? This step, that substitution, comes into play even when we have e's and exponents and stuff, okay? Anybody remember what this graph looks like? Like 3 over x or 1 over x, something like that.
I think it looks like half a parabola,
Yeah, kind of. It looks
but
something
sideways.
like this. There was actually a different conic section that I would say this looks like. Not quite the parabola. Yeah, if you kind of turn your head diagonally here, this is actually another way of writing a hyperbola. Okay. All right. Let's take a look at this last one here. Right? X of t equals square root of t. Now, separately, there's a +2. Okay, the +2 is not underneath the square root. And then we have y equals log t. All right. Keep those great ideas coming. What do we do? I mean, take some time to think first, of course, but what do we do? How do we get rid of the t's? I know logs were like the very first thing we learned this semester. Way back in August when it was still hot outside. Okay. So one of the things, there are many things that we learn about logs, but one of the things that I think is most useful about logs is remembering what the base is for something, right? So when we don't have a base, we call that the common log, and it really means base 10. But the other important thing about logs is remembering logs are the same as exponents, just in a different form. And so we can rewrite this as 10 to the y equals t, okay? And this right here, this rewrite in exponential form is no longer one of those, I learned about exponential functions one time and I didn't really get it, okay? It is, for better or for worse, something that comes up pretty frequently in the math that's to come in your future, okay? And so remembering how to rewrite logs and exponents in their forms is actually now one of those fundamental skills in your toolbox, okay? And so if that's something that you're like, ooh, this seems like super, super not clear to me, it might be something you want to work on a little bit over break just to refresh your memory, okay? All right, yes, 10 to the y equals t, okay? And so what can we do with this? Well, we can actually use substitution, right? We can take this, we can say x equals the square root of t plus 2, but everywhere we see a t, we can replace it with 10 to the y. And so we'll get x equals the square root of 10 to the y plus 2. Okay. Now, I will say that this one I chose this question more as a refresher for writing an exponential form than I did to say, let's get this in a familiar form. Okay, I don't know that this one really has a super familiar form. But what we do have is sort of problems that are all a little different in flavor, writing those parameters, eliminating those parameters. Okay. And so the last thing I want to leave you with is, this is all fine and good. I think there is something super important about being able to look at a question and in yourself go like, these are the skills that I know, let me try them out. Oh, this didn't work. I'm flexible enough to try a different idea. Doesn't mean I can't do it, just means it's a different idea. Okay. But for some of us who are more into patterns, all right, I need to make a couple corrections here. Here's a list of some common patterns that you see. All right. So I would read over these and see, look back in your notes like, oh, this X and Y example have the same degree. What did that give me here? Okay. Or if I saw something that kind of looked like this, what shape did that give me? Okay, so this right-hand column is blank for you to fill in some shapes if you're like, I would really like to know some patterns. Okay. Now, one way to do this is pattern matching from the notes, right? Because the examples from the notes are chosen so that we can see some of these patterns. But I did say we would come back to Desmos and we could take a look at how to use Desmos to graph parametric equations. Okay, so let me find my Desmos screen again. Okay, and I'm going to share my screen so that we can see the Desmos. All right, do we all see Desmos right now? Yeah, okay. So I'm going to get rid of this graph, right? This graph or this table just plotted points, which might be useful if you want to check your answers for plotting points. But here's how you can actually graph in parametric, okay? So I'm going to take example number 9, all right? And we said it was 3t minus 2, comma, t plus. Okay. So in the first spot, this is my x equation, my x of t. In the second spot, that's my blue equation or the y of t. Now, how come this is so short? Because you can change your parameters down here. So right now I just go from 0 to 1 for t. But let's say I wanted to go from 0 to 2. What do you think is going to happen if I type a 2 in here? Like, what's going to happen to our picture?
Become longer?
Okay, let's see. Ooh, yeah, it got longer. Okay, what happens if I put in an even bigger number? Gets even longer, right? Because we're letting the time, more time pass, right? 5 here means 5 seconds, whereas 1 is like 1 second. Okay. Or let's see, the one that had the 4, number 11, right? We had 4 sine t. And then we had 3 cosine t. What do you think the interval should be here so that I get the same picture that I sketched in number 11? Okay, usually a good guess, if I want to go all the way around object like that, 0 to 2 pi gives it to us. Okay, So this could be a great way for you to sort of check your work. If you're like, I'm not sure if this is a familiar form. Did I do it right? Did I do something illegal in my algebra? This is a good way to kind of check and make sure what you're getting is matching what you have in your algebra work. Okay. All right, so I'm going to stop sharing that screen.